Okay, let's look at the second one here. Not sure if we can model this with the pizza example again. I guess we can, even though it's physically probably impossible. First you eat one pizza. This is the first term, right? Then you eat... My pizzas are all going to be different sizes here. You know what I should do is... There's the first few anyways, right? There's the first few things in this sequence. Okay, aside from the fact that the pizzas are smaller than the previous example. The first time, if you proceeded to eat pizza like this, first you eat one pizza, then you eat two pizzas, then you eat 4 pizzas, next you would eat 8 pizzas, and 16, and 32. Obviously this is physically impossible as well. Unless you're the pizza eating champion of the world, and even then probably that would be questionable. If you did that, is this going to be the same? If you let this go on infinitely, is it going to have a finite sum the way the other one did? It doesn't. It clearly doesn't, right? Because what's happening with the numbers every time? Like the sum of the first 2 is 3. Then the sum of the first 3 is 7, right? That adds up to 7. This adds up to 15. If you think about the sums are 1, 3, 7, 15. The sum keeps getting bigger and bigger. Whereas the sum in the previous case was a half, then it was 3/4, then it was 7/8. Then it was 15/16, and then it was, 31 over 32. Like if you add all those fractions together, it's getting closer and closer to 1. It's kind of leveling off. If you looked at a graph of this first one, you have a half, then 3/4, then 7/8, then 15/16. It's kind of looking like that. It's leveling off at 1. Whereas this one, first you eat 1, then you got 3, then 7. This is going up to infinity here. This one does not have a finite sum. I'm not sure whether we want to turn this one into a pizza example, but first you eat one pizza. Now the negatives. First you eat, maybe we should do this one first because it's a little more physically possible. You eat half a pizza. Then you throw up a quarter of a pizza. Now the sum of this is how much happens to be in your stomach at any one time. I'm sorry. You eat half, then a quarter comes out, then an eighth goes back in because even though you just threw up a quarter of a pizza, for some reason you thought eating an eighth of a pizza sounded like a good idea. Then you throw up a 16th, then 1/32 goes in. Think about how much... Wow, this is crazy, I know. This does not happen in real life because pretty much if you throw up a quarter of a pizza, you don't eat pizza for a while, right? Because you don't like the sounds of it. Let's do a picture here, not of the actual event, but of this number. At first, you eat a half, so you get up to there, right? This is a half. Then a quarter comes out, so you go back to here, right? Then 1/8 goes back in. You go to there. Then a 16th comes out, so you get to there, right? So the line is just representing where is this going, okay? Instead of the arrows, let's use a line here. So let's draw some points of reference in here. Actually, first, let's draw, these are just reference points every quarter and an eighth and stuff, okay? Is that enough reference points here? This could potentially work. Let's see here. First, we're here. Okay, and then, oh no, don't do that. As soon as I said it's going to work, it doesn't work. Come on, it's not that hard. Okay, there, this will work. Okay, so you eat a half of it. And then you go back to a quarter, right? And then you go up another eighth. and you go back a 16th, and then you go up a 32nd, and then you go down this much, and up this much, and down this much. Where is it going to end up, sort of? In here somewhere, right? Does this have a finite sum? This right here. It does. Okay? This definitely does have a finite sum, and it's somewhere in here. As you keep going, what effect do these terms have? Do they have more and more of an effect, or less and less of an effect? They have less and less of an effect as the farther you go. The biggest event, either coming in or going out, was the first one here, right? This was the largest quantity of pizza, either positive or negative. As you go, each quantity of pizza is less and less, right? This is not much compared to the original amount. That's the significance. That's the same as this. The largest quantity of pizza in this one was the first part, right? A half was the biggest term in the sequence. By the time you get down here, this is hardly even worth opening your mouth for, right? Because 128th of a pizza, you can't even cut a pizza that small, right? This was the biggest piece, whereas down here, the pieces are getting bigger, right? The pieces being like more than one pizza, but the pieces are getting larger and larger here. Whether they're going in or out doesn't matter, right? What about this one? This is the hardest one to comprehend because I guess this is technically impossible. You can't eat a pizza and then throw up two pizzas, right? If we tried to make a graph here, because it's not going to work with the circle, if we tried to make a graph for this, this is the amount of pizza in your stomach. You're up at one pizza. That's the first term. This is the sum. Okay, this is how much we have here. So you go up to 1, then down to -1, right? Because 2 came out. Then you went up, 4? So you're up here. Then you're down here somewhere. Then you're up here. Then you're down here. What's happening with the number each time? It's getting bigger and bigger. Each term is getting more and more significant as far as you go. Whereas this one, each term is getting less and less significant the farther you go. It has to do with the common ratio. Okay? If the common ratio is a number, if the number part is smaller than 1, that would be kind of the everyday way of saying it. In this situation, R was -1/2. Whatever the previous term was, the opposite thing and half as much happens. Okay? That's what R being -1/2 here. I know it's kind of disgusting talking about this, but it actually goes a long way towards your understanding, I think. When you have the ratio being negative, it means whatever just happened, if half a pizza went in, now the pizza is going to come out, but half as much, right? And if pizza just came out, now half's going to go in. Half as much is going to go back in. A negative ratio means the opposite thing's happening. A positive ratio means the same thing is happening. If you just ate pizza, you're eating more, but it's half as much. This was 1/2. This was -1/2. The number part is smaller than 1. It has a finite sum. Infinite geometric series do have a finite sum when the number part is smaller than 1. Or if you want this mathematically, if the ratio is between 1 and -1. That's what that means. Between -1 and 1. Or if you're really clever and you understand absolute value, when you talk about the absolute value of something, you're talking about just the number part. Regardless of the sign, you're talking about the value of the number itself, regardless of whether it's positive or negative. It's really good when you highlight everything, right? Here's the important parts of this. I've highlighted them for you. The only thing I didn't highlight is if, or, the, and i.e. Okay? Whichever way you want to say that or remember it in your mind, when the number part is smaller than 1, regardless of whether it's positive or negative, the terms are becoming less and less significant. Terms become less and less significant. And then the converse of that, or the complementary or supplementary part of that is they do not have a finite sum when the number part is bigger than 1. Or in other words, the absolute value is bigger than 1. Or in other words, when the ratio is bigger than 1 or smaller than negative 1. Okay? For the reasons that we looked up there. If the terms are becoming more and more significant, which is what you could write right here, terms becoming more and more significant, I need to stop this. And then we'll look at where this formula comes from.